Hello and Assalamu alaikum. Welcome to a new podcast. Today we're going to talk about working with data. This lecture was made by one of my teachers, SM Jisanul Islam, for a course called MLSD or Machine Learning System Design, Spring 2026. At first, based on that resource, I made this notebook, and from this notebook, I generated this AI made video. Let's look at this at first.
Have you ever followed an AI tutorial, built this amazing model on a perfect data set, and then tried to make it work on real-world data, only to watch it just completely fall apart? Yeah, you are not alone. There is a huge gap between data in the lab and data out in the wild. So let's dive in and see if we can bridge that gap. It really all starts here with what I call the two worlds of data. See, in the research world, we get these pristine, static data sets. They're clean, they're perfectly labeled, and they let us focus on building cool new model architectures. But in production, whoa, it is the complete opposite. Data is a moving target. It's dynamic, it's noisy, it's full of missing labels and weird biases. The focus isn't just the model anymore. It's the entire data pipeline that feeds it. So how do the pros actually tame all this chaos? Well, they build a roadmap, right? A system for turning that messy, raw data into something a model can actually understand and use. And that roadmap, that's the machine learning data pipeline. Now, a typical pipeline has 5 key stages. First, you have to collect the raw data. Then you've got to store it somewhere, then process it to make it usable, version it so you can track all the changes, and finally, serve it up to your models. We're going to zero in on some of the trickiest and honestly most important parts of this whole journey. So let's start with storing the data. This choice is absolutely fundamental. Seriously, the way you decide to store your data literally defines its DNA. It dictates how fast you can get to it, what you can do with it, and really how efficiently your entire system is going to run. At the highest level, data kind of comes in 2 main flavors. You've got your structured data, that's the neat, tidy stuff that fits perfectly into rows and columns, like a spreadsheet of customer info. And then you've got the wild west of unstructured data. Images, audio files, social media posts, you name it. There is no neat grid. And that's where the real challenge, but also the real opportunity, really lies. Now, inside that unstructured world, you're going to hear a few key terms thrown around. Text data is pretty simple. It's just human language. Time series data are just readings taken over time, like stock prices. And multimedia data is exactly what it sounds like: images, videos, and audio. Just knowing these helps you pick the right tools for the job. And this brings us to a super crucial, very practical question. You've got your data, but what kind of file should you save it in? A CSV? Something else? Believe it or not, the answer can have a massive impact on your project's performance. Check this out, because this slide really shows the weakness of a format like CSV for big data analytics. Let's say you want to calculate the average sales. A row-based format has to read everything. It scans the product, the customer, the country, just to get to that one number at the very end of the row. And it does this for every single row. It's just incredibly inefficient. But a column-based format like Parquet, it's a total game changer. It stores all the values for a single column together. So when you ask for the average sales, it just zips right over to the sales amount column and reads only that. What's the result? Well, queries can be 10, even 100 times faster. This is exactly why it's the standard for large-scale analytics. So, how do you choose? Well, think of this table as your cheat sheet. CSV is simple and everyone can use it, so it's perfect for small files. But for huge analytics in a data lake, Parquet Speed makes it the clear winner. If you're deep in the TensorFlow world, TF Record is optimized just for you. And JSON is awesome because it's human readable and super flexible, especially with APIs. Okay, so we've stored our data efficiently. But remember, production data is dynamic. It's always changing. So how in the world do we keep track of it? We need to version our data, just like we version our code with Git. But why is this so critical? Well, first off, reproducibility. To recreate any experiment, you need the exact code and the exact data version you used. Second, debugging. If your model's performance suddenly tanks, versioning lets you trace the problem back to the specific data change that caused it. It also lets teams collaborate without tripping over each other, and it gives you an audit trail for compliance. These aren't just suggestions, they are lifesavers.
And the tool that makes all this possible is DVC, or Data Version Control. And the simplest way to think about it is right there on the screen. It is Git, but for your data. It's an open source tool that works right alongside Git to track your massive data sets without trying to stuff huge files into your code repository.
And if you've ever used Git, the workflow is going to feel just like coming home. You initialize DVC, you tell it which data to track, and then Git just handles a tiny little pointer file, while DVC pushes the actual heavy data off to cloud storage. It's a really elegant way to keep your data and your code in perfect sync.
All right, let's move on to the next critical stage in our pipeline, processing. And this is where we hit one of the biggest bottlenecks in all of machine learning, getting high-quality labels for our data.
I love this analogy. Unlabeled data is just a pile of raw information. It's like a shoebox full of old photos. You can see the faces, but you have no idea who they are or when the photo was taken. Labeling is the act of going through that box and writing the names, the dates, the places on the back of each one. You are literally turning raw data into structured knowledge. So there are two main ways to get this done. You can have humans do it all by hand, which gets you amazing quality but is very slow and very expensive. Or you can use programmatic approaches, writing rules or using other models to generate labels automatically. This is way faster and cheaper, but the labels can be noisy or a little less accurate.
Now, this is where it gets really interesting. Look at this chart. This is such a great example of a real-world problem. How would you even begin to label these squiggly lines as normal or anomalous? And what if the event you actually care about, like a fraudulent transaction, is incredibly rare? Like it happens less than 1% of the time. This leads to a huge challenge.
And that challenge has a name. It's called class imbalance. It's what happens when one class, like fraud, is a tiny little needle in a giant haystack of not fraud examples. Any model you train on this data will get really, really good at predicting the majority class and almost completely ignore the rare but critical minority class. So, how do we fight back? Well, there are two main strategies. At the data level, we can actually generate more examples of that rare class using techniques like SMOTE. At the algorithm level, we can tell our model to pay way more attention to the minority class by penalizing mistakes on it more heavily. Most frameworks, like scikit-learn or TensorFlow, have a simple class weight parameter you can just set to balanced to do this for you.
As we wrap up, I want to come back to this quote. This is the core truth of production machine learning. The fanciest model in the world is completely useless if you can't reproduce your results. Managing your data with deliberate processes and tools like DVC is just as important, if not more so, than the model architecture itself.
So I'll leave you with this final thought. Imagine this scenario. You're facing a real-world problem. Your model is outdated, your resources are tight. What do? Do you try to get more expensive hand labels? Do you use programmatic labeling to adapt quickly? The right answer? Well, it depends on everything we've just discussed. Thanks for joining me.
After this visualization brief explanation, we are gonna move to uh, our podcast. There will be two hosts, two AI hosts, and it's gonna be an interactive podcast where I can also go alone with the hosts to ask questions and clarify my doubts. So let's start.
So imagine a machine learning model hits like 99.95% accuracy,
Oh, wow. Yeah.
right? In almost any other engineering discipline, you look at a metric like that, you pop champagne, and you immediately ship it to production.
Right, because the expectation is that precision is absolute, like a clean A plus.
Exactly. But when you step into the actual, the machinery of production data science, that A plus can be completely meaningless. Like, in fact, a model with 99.95% accuracy can actually be utterly useless.
I mean, it is the ultimate statistical mirage. And what's wild is that the reason for this illusion it has very little to do with your neural network architecture.
Right.
And it has everything to do with the unseen plumbing. It is entirely hidden in how we store, how we label, and how we balance our data before the model ever even sees it.
Yeah. So welcome to this custom-tailored deep dive. For you, the listener, our mission today is to bridge this massive, sometimes frankly terrifying gap between the pristine, perfectly organized data used in academic research and the absolute chaos of real-world production data.
The trenches, basically.
Yeah, exactly. And our guy. So imagine a machine learning model hits.
Sorry for
So
the interruption.
imagine a machine learning model hits like
Come on.
99.95% accuracy,
Oh, wow. Yeah.
right? In almost any other engineering discipline, you look at a metric like that, you pop champagne, and you immediately ship it to production.
Right, because the expectation is that precision is absolute, like a clean A+.
Exactly. But when you step into the actual, the machinery of production data science, that A plus can be completely meaningless. Like, in fact, a model with 99.95% accuracy can actually be utterly useless.
I mean, it is the ultimate statistical mirage. And what's wild is that the reason for this illusion has, well, it has very little to do with your neural network architecture.
Right.
And it has everything to do with the unseen plumbing. It is entirely hidden in how we store, how we label, and how we balance our data before the model ever even sees it.
Yeah. So welcome to this custom tailored deep dives. For you, the listener, our mission today is to bridge this massive, sometimes frankly terrifying gap between the pristine, perfectly organized data used in academic research and the absolute chaos of real-world production data.
The trenches, basically.
Yeah, exactly. And our guide through this is a highly detailed set of university lecture slides titled Working with Data. This is from a spring 2026 course, DS 4491, taught by SM Jishanul Islam.
It's a fantastic resource.
It really is. Okay, let's unpack this. We are going to figure out exactly why that 99.95% accuracy is a crap. But to get there, we really have to follow the life cycle of a piece of data from the wild all the way into the model.
Which requires unlearning the textbook approach to data science, like entirely.
Right, because if you are training a model in academia, you're usually operating in a heavily curated laboratory. You download something like the MNIST data set, the handwritten digits.
Yeah, the classic, it is static, it's pre-clean, every single label is perfect.
Right.
Your entire focus is just tweaking your Python code to get the best inference. But moving from that environment to production data,
It's like leaving a masterclass kitchen, right, where the sous chef has pre-measured all your ingredients into little glass bowls for you. And then suddenly you're trying to cook in a food truck during a hurricane.
that is exactly what it feels like.
Because we don't need to spend time defining basic data types for you. Like if you're working in MLOps, you already know the difference between, say, a continuous numerical value.
Like a temperature reading.
Right, exactly. And a binary categorical label, like yes or no. The real shock is the actual structure of the data hitting that food truck.
The hurricane itself, you have highly structured CSV tables just slamming into completely unstructured multimedia raw text streams from NLP pipelines and semi-structured JSON files that frankly don't adhere to any strict schema at all.
Yeah, it's just a mess. So since production data is this hurricane, the immediate next question is, how do we possibly store and organize this mess efficiently?
Right, which immediately forces a fundamental architectural decision. How do you physically store it so you can actually use it for analytics later? And this is where the split between row-based and column-based formats becomes absolutely critical.
Yeah, because most developers, they just default to what they know, right? CSVs or JSON arrays. And those are row-based.
Correct.
If you have a massive data set of, say, e-commerce transactions, a row-based format stores all the information for a single transaction together in continuous memory. So your product ID, customer name, timestamp, and sales amount are physically written next to each other at a disk.
Which is, terribly inefficient for analytics.
Really? How so?
Well, let's say your data science team just wants to calculate the average sales amount across, say, 10 billion transactions to establish a baseline feature.
Okay, that's a lot of rows.
Exactly. If you use a row-based format, the dist head has to read through every single piece of data in every single row. The names, the timestamps, the products, all of it, just to extract that one sales number from each line. It is an immense amount of wasted disk I/O.
Oh, wow. Yeah, so it's reading tons of data it doesn't even need. That's where column-based formats like Parquet come in, right?
Exactly. Parquet stores all the values for a single column together. All 10 billion sales amounts are written sequentially.
So when you run that same query for the average sales, the system just completely ignores the customer names and the timestamps.
Right. It just reads the continuous block of sales data. Plus, because data in a single column is highly similar, it's just a bunch of floats. Parquet can apply these really aggressive compression algorithms, saving just massive amounts of storage.
Wait, okay, hold on. If column-based Parquet is so heavily optimized for read-heavy analytics and compression, why are we still touching CSVs or JSON at all? Like, why not use Parquet for absolutely everything in production?
Ah, right operations.
Okay.
Think about a high-frequency trading app or a live web server. The system is constantly generating single new events. Appending a single complete transaction to the bottom of a row-based CSV is incredibly fast.
Right, you just drop it at the end of the file.
Exactly, but if you try to append one transaction to a column-based format, you effectively have to crack open and rewrite every single column structure. You are rewriting the entire file just to add one event.
Oh man. Okay, so row-based formats are for write-heavy transaction streaming, and column-based formats are for read-heavy analytics.
You got it. And the sources also mention some really specialized formats like JSON lines.
Oh yeah, which is great because it allows you to stream massive data sets line by line so you don't completely blow up your RAM trying to parse like a 50 gigabyte JSON array all at once.
Exactly. There's also TF record, which is TensorFlow's binary format. That one actually physically interleaves different data types, so like an image and its text bounding box coordinates.
Right, so the GPU can pull them into memory simultaneously without bottlenecking. That's super smart.
It is. Now, once you've chosen these formats, they have to physically live somewhere. And in a modern data pipeline, an engineer usually manages the lifecycle across 4 distinct storage locations.
Okay, let's break those down.
Sure. So raw, unstructured data from the wild is dumped directly into a data lake. Think Amazon S3 or Azure Blob. It's just cheap, infinite object storage.
Right, then you have relational databases, your PostgreSQL or MySQL setups. This is where you keep the highly structured, mission-critical stuff like user account balances. Because the key requirement here is ACID compliance.
Yeah, and a lot of people throw around the ACID acronym: atomic, consistent, isolated, durable, without really unpacking the mechanism. Let's just look at atomic, for instance.
Okay,
It means a transaction is all or nothing. If a script updates a user's balance but crashes before updating the transaction log, the database rolls the entire operation back.
so you don't end up with half-processed, corrupted data.
Exactly.
From there, the clean, structured data often moves into a data warehouse like Google BigQuery, which is specifically tuned for business intelligence workloads. But the storage concept I found most fascinating for machine learning specifically is the feature store, like Feast or Tecton.
Oh, absolutely. Because feature stores solve a very specific, incredibly painful problem in production AI, which is training serving skew.
Right.
Imagine a data scientist writes a complex SQL query to calculate a user's, say, average click rate over 30 days, and they use that to train a model offline.
Okay, makes sense.
But when that model goes live, the backend engineering team has to rewrite that exact same logic in Java to calculate the click rate in real time.
Oh, I see where this is going.
Yeah, if the Java code and the SQL code don't perfectly align, which they almost never do, the model gets slightly different data in production than it saw in training, and its performance just degrades.
So a feature store acts as like a centralized vault. You calculate that average click rate feature once, store it in the vault, and both the offline training pipeline and the live production model pull from the exact same source. No skew.
Exactly. The storage architecture is solved. But of course, this introduces the next major crisis in the pipeline.
Naturally.
Because once data is sitting in these lakes and warehouses, it isn't static. It updates daily, columns are added, schemas change, bad data gets dropped. What happens when, say, a junior engineer accidentally overwrites a critical data set in S3 and suddenly your production model's accuracy tanks?
Yeah, if you don't have a way to roll back to the exact data state from last Tuesday, you cannot Oh, hey there, how can we help?
So I have a question for the previous topic. You're talking about a workflow. Like at first, all the raw data comes to data lake, then it goes to relational database, then the structured, really good data that we need goes to the data warehouses. But where does feature stores come here? Like in which part do we actually store the data in the feature stores? Okay, so my question was for the last topic actually. We are talking about workflow for different storage systems. You said that at first all the raw data goes to the data lake, then from there they go to the relational database, and after that all the structured data goes to the data warehouse. Now my question is, where does the feature stores come here in this picture? Like, how do we actually use feature store to store the data in this workflow?
That is a fantastic question, and it really highlights the complexity of modern data architecture.
Absolutely. Think of the feature store as sitting across that whole workflow, not just at one step.
Yeah, it's not strictly sequential like the data lake to data warehouse movement.
The feature store is there to serve features, which are the outputs of your processing steps, back to the models.
So raw data starts in the data lake, then the data warehouse is where you clean and transform that data into a usable format, right?
Correct. That transformation process, the cleaning, extraction, aggregation that creates the features.
The feature store then acts as the central, standardized publishing location for these derived features.
For example, the data warehouse might calculate the average click rate over 30 days we mentioned earlier.
That calculated value, that feature, is then pushed to the feature store.
So now both your offline training environment and your live prediction service can pull that single consistent number.
It bridges the gap between the analytic workload of the warehouse and the real-time serving need of the live model.
It's all about consistency, avoiding the training serving skew that would otherwise completely ruin your model performance.
Oh, back to our listener. What's up?
Give me a real world scenario where a data in a specific field, a data goes through all these workflows or all these storage system, and how does it actually be processed and goes through all this storage system, and how does it actually um, get stored before getting used in the models.
That is a phenomenal request.
Okay, let's walk a single piece of data through this whole system.
Let's use the fraud detection system we mentioned earlier.
A good real-world example, because it's messy.
Imagine a user swipes a credit card. That generates an immediate transaction event.
That raw single-line event is unstructured, like a log file, so it gets dumped straight into the data lake S3.
Simultaneously, the bank's core system has to update the account balance, which requires ACID compliance.
So that clean, critical update goes into the relational database.
Later that day, an ETL pipeline runs to analyze all the transactions.
That pipeline pulls data from the lake and the database, cleans it, and aggregates it.
It calculates features like this user's average transaction amount over the last 3 days.
That aggregated, clean data then lands in the data warehouse BigQuery ready for massive analytical queries.
Now, here's where the feature store comes in.
The moment that average transaction amount is calculated, it's pushed to the feature store.
When the live model needs to decide if the next swipe is fraud, it pulls that average transaction amount feature from the feature store.
It's all about ensuring that calculation is consistent everywhere.
That feature is what the model uses to make its prediction, bridging the gap between historical analysis and real-time decision.
That's a great example of the full journey.
Performance. Now, let's get back to the versioning issue.
Yeah, because we solved the storage architecture, and now we need to solve the problem of data mutation.
Because once data is sitting in these lakes and warehouses, it isn't static. It updates daily.
Exactly. Columns are added, schemas change, bad data gets dropped.
So what happens when, say, a junior engineer accidentally overwrites a critical data set in S3, the data lake?
Yeah, if you don't have a way to roll back to the exact data state from last Tuesday, you cannot debug the problem, especially in our fraud system.
Right. If you cannot reproduce the data that led to a drop in performance, you're sunk.
So what does this all mean? Well, it leads to the versioning step of the MOps pipeline.
And the tool the lecture focuses on is DVC data version control.
It functions like Git, but it's engineered specifically for massive machine learning data sets.
Because anyone who has used standard Git knows the golden rule.
Never, ever commit a 50 gigabyte CSV file to your repository.
Oh yeah, the repository will just bloat, clone times will become hours, and the whole system will eventually crash.
Git tracks line-by-line text changes. It is fundamentally not designed for massive binary or tensor files.
But DVC solves this through this brilliant separation of concerns.
When you track a massive data set with DVC, it doesn't actually put the data into Git.
Instead, DVC generates a tiny text file, a .-dvc file, that contains an MD5 hash.
Right, which is essentially a unique fingerprint of your data at that exact moment in time.
Exactly. You commit the tiny text file to your Git repository.
And DVC secretly moves the massive 50 gigabyte data file into remote storage. like an S3 bucket.
So DVC is like keeping a lightweight restaurant menu in your pocket.
The menu just tells you what the dish is. That's the .dvc file.
But the actual heavy ingredients are kept in an industrial warehouse out of town.
You don't carry the warehouse in your backpack. I love that analogy.
That mechanism is incredibly elegant.
And practically speaking, when you are collaborating with a team and you want to pull down a specific version of the data, DVC gives you two distinct commands.
And they operate very differently under the hood. DVC checkout and DVC pull.
Okay, let's quickly recap those.
If you run DVC pull, DVC looks at the hash in your Git repository, connects to the remote S3 bucket.
And literally downloads the missing 50 gigabyte file over the internet.
It's pulling the ingredients from the warehouse.
Exactly. But DVC checkout is completely local and practically instantaneous.
And let's explain why it's instantaneous, because this is a really great OS level trick.
DVC keep a hidden cache folder on your local machine.
When you run DVC checkout to switch between dataset versions, it doesn't copy gigabytes of data back and forth.
Right.
It uses hard links. It just updates the file pointers in your operating system.
To look at the correct files that are already sitting in that hidden cache.
It takes 0 extra disk space, and it happens in milliseconds.
And this versioning discipline gives you absolute reproducibility.
You can pair a specific Git commit of your Python code with the exact .dvc hash of your dataset,
And perfectly recreate any historical experiment.
which is huge for compliance.
Like if you are in finance or healthcare, you have a rigorous audit trail.
Proving exactly what data was used to train a specific model version. Exactly.
Okay, so the data is properly stored, it is perfectly versioned, and the pipeline is robust.
But if you are building supervised machine learning models, literally none of this matters yet.
Nope.
Because a 50 gigabyte tensor file is just noise, unless it has labels.
Welcome to the single most agonizing bottleneck in the entire production pipeline, the labeling crisis.
Yeah, let's talk about the economics of this.
The gold standard is obviously hand labeling by subject matter experts.
But if you are building an AI to detect rare anomalies in, say, MRI scans, you can't just outsource the labeling to an inexpensive click farm.
No, due to HIPAA constraints and the required medical expertise.
You have to pay actual radiologists to sit at a computer and draw boxes on hundreds of thousands of images.
It is financially devastating and incredibly slow.
Yeah, and beyond the cost, you also run into label multiplicity.
Right, this is when two highly paid experts look at the exact same data point and completely disagree on the label.
The guidelines become subjective. Annotator fatigue sets in.
And suddenly your really expensive ground truth dataset is just riddled with noise.
Now, the inverse of this expensive process is using natural labels.
This is organic user behavior.
Like, if you run a streaming service and recommend a movie, and the user clicks play, the system automatically logs a positive label.
It's practically free and massive in scale.
But natural labels suffer from severe latency and ambiguity, right?
Oh, absolutely. A click is immediate, but what if your label depends on a user actually buying a product and not returning it 30 days later?
Your model is flying blind for a month, waiting for the ground truth to actually settle.
Plus, organic behavior is deeply biased. Users often just click the first item in a list, regardless of its actual relevance.
So when human experts are too expensive and natural labels are too noisy, the industry turns to programmatic solutions to generate labels.
The slides cover 4 major techniques here, and understanding the mechanisms behind them is really crucial.
Let's start with weak supervision.
What's fascinating here is how weak supervision, which is often implemented through frameworks like Snorkel, relies on heuristics.
Instead of hand labeling 100,000 emails as spam or not spam, a domain expert writes dozens of simple rules.
Like regular expressions, keyword searches, or simple scripts.
Exactly. For example, if the email contains the word urgent and a crypto wallet address, label it as spam.
Now, obviously, those rules aren't perfect. They will mislabel some normal emails.
But Snorkel uses a generative model to analyze where these different rules overlap and conflict.
Mathematically estimating their accuracies, and then it assigns probabilistic labels to millions of data points in a matter of hours.
You trade pristine quality for massive volume, and the neural network basically learns to look past the noise to find the underlying patterns.
Right.
Another approach is semi-supervised learning.
You take a tiny sliver of data that you did pay humans to label, and you train a basic model.
Then you unleash that model on the massive mountain of unlabeled data to generate pseudo-labels.
So you are banking on the assumption that these structural clusters in the data are strong enough that the basic model's guesses will be mostly correct.
Exactly.
Then there is transfer learning, which is honestly the backbone of modern AI.
Let's say you want to build a model to detect a specific type of manufacturing defect on an assembly line.
But you only have 500 labeled images of the defect.
Training a deep neural network from scratch on 500 images will fail miserably.
Yeah, so you don't start from scratch. You download a massive pre-trained model like ResNet.
Which has already been trained on millions of generic images from the internet.
The early layers of that neural network have already learned how to detect fundamental concepts.
Edges, shapes, textures, lighting.
You literally freeze those foundational layers so their mathematical weights can't change.
Then you only retrain the finally few classification layers at the top of the network using your 500 specific defect images.
You transfer the generalized knowledge, which radically reduces the number of labels you need.
Right, and the final technique is arguably the most elegant way to utilize human experts, active learning.
Instead of having a human randomly label thousands of images, the AI model itself acts as the filter.
Right, so it scans the unlabeled data and selectively asks the human to label only the examples it is least confident about. It's called uncertainty sampling.
Exactly. If the model looks at an image and its internal probability is 99% sure it's a dog, it labels it automatically.
But if it looks at a blurry image and is 51% sure it's a dog and 49% sure it's a mop, it kicks that specific image to the human annotator.
By focusing human effort exclusively on the hardest edge cases, active learning can slash labeling costs by an order of magnitude.
2 to 10 times cheaper, easily.
So, okay, you've versioned your data, you've used programmatic techniques to label it efficiently, and you finally train your model.
And the console spits out that glorious metric, 99.95% accuracy.
Which brings us all the way back to our opening hook. Why is this a total lie?
Because you've just slammed headfirst into class imbalance.
Yeah.
Let's look at the classic use case, credit card fraud detection, tying back to our scenario.
You have a massive data set of transactions, but fraud is incredibly rare.
Let's say only 0.05% of transactions are actually fraudulent. The labels are wildly disproportionate.
And neural networks are fundamentally lazy, right? They look for the mathematically easiest way to minimize their error rate.
Precisely. If a model looks at that highly imbalanced data set, it quickly realizes a shortcut.
If it ignores the complex features entirely and simply guesses not fraud on every single transaction it ever sees, it will be right 99.95% of the time.
The model achieves 99.95% accuracy, but it catches exactly 0 cases of fraud.
Accuracy, as a metric, completely obscures the failure.
This is why no data scientist trusts accuracy in production.
You have to evaluate the model using metrics that actually understand the imbalance.
Right, like precision, which asks, out of all the transactions the model flagged as fraud, how many were actually fraud?
And recall, which asks, out of all the real fraud that existed, how much did the model manage to catch?
The lectures live strongly advocate for RORA, the area under the receiver operating characteristic curve.
And AUPRC, the area under the precision recall curve.
But let's actually explain how these work, because people throw these acronyms around constantly.
How does looking at the area under a curve solve the accuracy lie?
Well, normally a model outputs a probability between 0 and 1.
By default, we set a threshold at 0.5. Anything above 0.5 is fraud, anything below is safe.
But evaluating a model at just one arbitrary threshold doesn't tell you how well the model actually understands the data.
Okay?
The ROC curve plots the model's true positive rate against its false positive rate across every possible threshold simultaneously.
So the area under that curve is effectively a single number representing the model's fundamental separating power.
Exactly. Mathematically, the ROC tells you the probability that the model will score a randomly chosen positive instance higher than a randomly chosen negative one.
It completely ignores the class imbalance because it measures ranking ability, not raw accuracy.
That makes so much sense.
And AUPRC does something similar but focuses almost entirely on the minority class, making it even more sensitive to rare events like fraud.
Right. So once you've identified the imbalance using the right metrics, you have to fix it.
We have two main approaches, data level fixes and algorithm level fixes.
On the data level, you could just randomly delete normal transactions until the scale's balanced, that's undersampling, but you throw away valuable training data.
Or you could oversample, randomly duplicating the rare fraud cases.
But if you just feed the network the exact same 5 fraud images 1,000 times, it just memorizes them, it overfits.
Right. To solve this, the industry standard is Smoot synthetic minority oversampling technique.
But we have to address the elephant in the room here.
If Smoot is synthesizing new data points, aren't we basically hallucinating data into our production pipeline?
How can a model learn reality from synthetic data?
It sounds like hallucination, but the mechanism is strictly grounded in the existing data.
SMOTE operates in the feature space using key nearest neighbors.
Okay, so what does that look like?
Imagine you plot your rare fraud cases on a multidimensional graph based on their features,
SMOTE draws a line between one known fraud case and its nearest fraud neighbor.
and then randomly generates a new data point somewhere along that exact line.
So it's interpretation. It's essentially teaching the model that fraud isn't just these two specific points, but the continuum between them.
It expands the decision boundary organically.
Exactly. But let's say you don't want to synthesize data.
You want to leave the data set completely untouched.
You can move to algorithm level fixes where you change the math of how the model learns.
Right, the most common is cost-sensitive learning,
In frameworks like scikit-learn, you might set a parameter like class weight equals balanced.
which means you are literally hacking the loss function.
You tell the model, if you misclassify a normal transaction, your penalty is tiny.
But if you miss a rare fraudulent transaction, the mathematical penalty is massively multiplied.
You literally force the network to care about the minority class.
Exactly. A more advanced version of this is focal loss.
Originally designed for object detection in images where the background vastly outnumbers the target object.
The mechanism of focal loss is brilliant.
As the model trains, it dynamically scales the loss based on its own confidence.
If the model looks at an easy, obvious example of a normal transaction and gets it right, focal loss squashes the gradient update down to near zero.
The model learns nothing new.
Right, but if it encounters a hard, borderline case of fraud and gets it wrong, the loss isn't squashed.
The network focuses all of its mathematical updates on the hardest problems in the dataset.
So if we step back and look at the entire journey outlined in these lecture slides,
We started by abandoning the illusion of pristine research data and diving headfirst into the production hurricane.
we bypassed row-based bottlenecks by storing analytics data in column-based Parkin.
We maintained sanity over mutating datasets by using DVC to create hard-link pointers in a Git repository.
We hacked the labeling crisis using uncertainty sampling in active learning.
And finally, we dismantled the 99% accuracy lie by fundamentally shifting our metrics to Auroch and dynamically scaling our gradients with focal loss.
The entire progression proves one inescapable reality of modern AI.
The smartest neural network in the world is completely at the mercy of the data pipeline feeding it.
But, looking at how we build these pipelines today introduces a really provocative thought about tomorrow.
Let's hear it.
We discussed how natural labels tracking organic user behavior like clicks and views are the cheapest way to train models at scale. But as the web becomes saturated with AI agents, bots scraping data, summarizing articles, and clicking links on behalf of humans,
Those natural labels are being contaminated.
what happens to our vast data pipelines when the organic user behavior we are capturing is actually just the output of other bots?
Oh, wow, that's incredible. If your models are training on bot behavior, optimizing to predict the actions of an AI that is trying to mimic a human,
The entire pipeline becomes this closed loop of synthetic reality.
the 99% accuracy lie was about imbalanced math. The next accuracy lie might be about whether a human was even involved in the data at all.
That is a completely wild thought to leave off on.
We encourage you to really look under the hood of the pipelines you interact with.
And keep questioning the data around you, especially the next time someone promises you perfect accuracy.
Thanks for joining us on this deep dive.
So that was it for this podcast. Bye bye. Allah Hafiz.